Friday I demonstrated doing differentiating from first principles. But you don't always have to differentiate from first principles. In fact, we like to avoid it if we possibly can, because it's a bit of a pain differentiating from first principles. So here is a key thing in the context of the work we'll be doing in the course. If differentiability is in doubt, differentiability is in doubt, then we have to differentiate from first principles. Okay, and we'll be doing a bunch of examples like that when we get to differentiability. If we are confident that the function is differentiable, we can simply use differentiation rules. I just need to get the zoom correct on this. I was fiddling around with it on Friday, and now it's not how it normally is. That's 150, but 200 is too big, isn't it? Come. Or is that what we normally have? I think it's a bit too big. Let's try 180. 180. Does that look good? Well, let's just try 180 and see what it looks like. Come on, go. That looks alright, I think. Okay. I shrank it, I think it was on Friday, so that I could fit an entire example on the screen, and then I couldn't remember what it had been before. Okay, if we are confident that function, we can simply use differentiation rules. Yay! So let me demonstrate. So when you're using differentiation rules, all your rules that you derived and learned last year still apply. But the trick is that there'll be two variables sitting there in the function, and you're only ever differentiating with respect to one at a time. So you need to keep in mind which variable is the one with respect to which you're differentiating, and any other variables that are present, you just have to hold constant. So you kind of pretend that they're like a 2 or a k or something, and they don't take part in the differentiation. Okay, so I'm going to demonstrate with exercise. Oh, I've written here 76. I didn't mean 76. I meant 80. I apologize. 76 is what I did on Friday. 80, there we go. It says find dz by dx and dz by dy for the following function. So here we've got z equals xy plus x squared y. Could you please keep quiet? Now I promised somebody, it's a big class, hard to pick people out. I promised somebody on Friday, I think, that I would do one of these by first principles, and I'm not finding the person. But I haven't done that. So I know that I owe one of you some work. Okay, so it's school holidays, by the way, and my children are going to be spending the bulk of the next 2 weeks in my office watching YouTube. Some days my husband's working from home, and other days they're in holiday care. It's all very complicated. So I'm bringing my phone with me just in case there's any disasters. Okay, all right. So I apologize. Normally I wouldn't be checking my phone during a lecture, but I just want to make sure things aren't exploding. Exploding children, don't want exploding children. Okay, all right. So dz by dx. So dz by dx means we're going to differentiate this thing with respect to x while holding y constant. So the y behaves just like it would if it were a number like 2. Okay? So if you differentiate 2x, you get 2, right? So if you differentiate xy, you get y. And then over here, x squared y is just 2xy. And the y doesn't go away. It's still present, but it's present in exactly the same way that a constant would be. What about dz by dy? Similar, but now we're differentiating with respect to y. We need to hold the x constant. So if we differentiate xy, we get x. And if we differentiate x squared y, we get x squared. Okay. It's really not hard. Differentiation is easy. Ordinary differentiation is easy. Partial differentiation is just as easy. It just takes a little bit of a, I don't know, you just need to train your mind to be able to only see one variable as the variable, and then in the very next line you have to flip it. It's the other one that you're considering. So there we go. Z equals cos x sine y plus 3y. Okay, so dz by dx is going to be minus sine x sine y, and then the plus 3y, that's just plus a constant as far as x is concerned. So when you differentiate it, you just get 0. So that plus 3y just disappears when you're differentiating with respect to x. But if you're differentiating with respect to y, of course, it sticks around. So what will that be? That'll be cos x cos y plus 3. Okay, could you please keep quiet? C, what is C? Z equals y over x plus tan x. So dz by dx is what? Notice how all the d's that I'm writing are curly d's. Okay, don't write an ordinary d. An ordinary d is only used in ordinary differentiation when your function is a function of only one variable. As soon as your function is a function of more than one variable, you have partial derivatives. And you can imagine, if you're using calculus to actually describe some real life situation, there's invariably more than one variable involved, because the world's like that and life's like that. So partial differentiation out there in actual uses of calculus in context, differentiation is almost always partial differentiation. And then have you encountered differential equations in your first year course? Most real life differential equations are partial differential equations, not ordinary differential equations. You've seen ODEs, but most differential equations in context are PDEs. Yes?
For question B, where you're differentiating with x, what happens with 3y?
The 3y. The 3y went poof and disappeared because we were differentiating with respect to x. And as far as x is concerned, in the context of partial differentiation, 3y is just a constant. So that would just be like a plus 10. And if you differentiate plus 10, you get zeros. You differentiate plus 3y, you get 0. But then when we do the y derivative, then suddenly that 3y is not a constant. It's actually involved in the differentiation. Does that make sense? Cool. It takes a bit of getting used to, because y is a variable. It is a variable. But when you're doing x, the x derivative, you hold it constant. Okay, so differentiating with respect to x. So let's have a look. When you differentiate 1 over g, remember from first year you get minus g dash over g squared. So this would be minus y 1 plus sec squared x over x plus tan x squared. Yeah, well, basically this is quotient rule. It is quotient rule, but the derivative of the numerator is 0, because the numerator is a constant. If you go back and look in your differentiation rules from first year, you probably did this one first, just before you did quotient. If you were taught in the same order in which I teach first year maths, you would have done product rule, then you would have done this as a special case of quotient rule, and then you would have done quotient rule itself. And then dz by dy. Now it's the denominator that's the constant, it's the numerator that's the variable. So this is just basically like we're differentiating y over 2. And the derivative of y over 2 would just be 1 over 2. So there you go. It's kind of strange, isn't it? It's kind of strange, because all the differentiation rules are all the ones you've always used. But you just have to do that little trick of considering one variable to be constant. You give it a go. Try any one. And notice how I've mixed it up with the notation. In 80, I use the curly D notation, but in 81, I'm encouraging you to use the little subscript notation, but they're exactly the same. Little subscript x is the same thing as d by dx. Okay, all right. So I said a minute ago, I'm going to move on to higher order partial derivatives, but in fact, first, before I do that, I'm going to use partial derivatives in a quite specific context. We can use partial derivatives. We can use partial derivatives to find tangent lines to curves of intersection there shouldn't be an S there, of two surfaces if one surface is x equals k or y equals k. In other words, a vertical plane. And rather than write lots of words, this is best demonstrated with an example, so I'm going to demonstrate with exercise 83. It says, use partial derivatives to find the parametric equations of the line tangent to the curve of intersection of the graph z equals x squared plus 3y squared. So that's an elliptical paraboloid. And the plane y equals 2. Okay, and then they give us a point, x equals 1, y equals 2. Alrighty then, so these two surfaces, the elliptical paraboloid and this vertical plane, intersect and they have a curve of intersection and we're wanting a tangent line. So now the reason why partial derivatives can help or can get us to the answer is because the curve of intersection, by definition, satisfies both plane equations. You can basically see these two surfaces and you can see the curve of intersection as being drawn on your surface with a Koki, okay? So the curve is drawn onto the surface of the paraboloid, but it's also drawn onto the plane, okay? So because our curve sits on the plane y equals 2, it means in the context of our, so here we go, here's our origin, there's the x-axis, there's the y-axis, here's the z-axis, and we've got this plane y equals 2 that's slicing through this elliptical paraboloid. And so our curve, what will our curve be looking like? Our curve will be some sort of, it'll be some sort of parabola, maybe hyperbola, but on the y, it'll be on the y equals 2 plane. So that curve of intersection lies on the y equals 2 plane, okay? And the tangent line will therefore also be on the y equals 2. So along our tangent line and along our curve, y is not changing. Y is constant. And so our x partial derivative is going to give us the slope of our curve because our y value is not changing, but our x is. And so that's the x partial derivative, because the x partial derivative says, what if we hold y constant and just let x change, what's our slope? So, yes?
Say if you have to sum your y value in first, would you still have to use your partial derivative even though you only have one variable?
Okay, so there's an interesting question. So if you sub y equals 2 into that paraboloid equation, your paraboloid equation becomes an expression with only one, well, two variables, I suppose, z and x, but z will be a function of x only. So do you still have to use the curly D rather than the ordinary D? I'd still be inclined to use the curly D because fundamentally we're still dealing with a function of two variables. But yeah, that's an interesting way of looking at it. Now in this context, still use the curly D. That made me think. I like questions that make me think. Okay. Along the curve of intersection, I'm just going to write what I've just said verbally. Along the curve of intersection, y is constant. The x derivative will give us our slope. But there's a little funny bit coming up. So let's have a look. dz by dx is 2x. dz by dx evaluated at x equals 1 is therefore 2. Okay? Yay, we've got our slope. However, how does that actually help us answer the question? Because the question wants the equation of the tangent line, and it wants the equation of the tangent line in parametric form. So how is that slope equals 2 going to give us our parametric equations? And here, I want you to think about what that number 2 means. Okay, if we have a secant or a little tangent and we want to work out the slope of that little line segment there, it's vertical over horizontal, right? It's delta z over delta x. Y is not changing. Rise over run, or whatever the terminology is that you like to use. But it's basically the vertical distance over the horizontal distance, and that will give us our slope. So, if let me move my little box here. So if I have a delta x of 1, okay, that dz by dx is the slope. Okay, my slope is 2. I've just worked it out. That's my dz by dx. Okay, my slope is 2. My slope is delta z over delta x. If I fix my delta x to be 1, then that must mean that my delta z equals 1, equals 2. And the reason why that is a useful way of looking at it is that allows us to parametrize our line. Let me rather stick with x and lambda, seeing as we're talking about a straight line. It doesn't really matter. I tend to use x and lambda when I'm talking about straight lines, but really, it's not a big deal. We've been given a point, x equals 1, y equals 2. We haven't been given the z value. Let's work it out. If x is 1 and y is 2, I've got 1 plus 3 times 4, 1 times plus 12, it's 13. Plus lambda, what's my direction vector? Well, I know that the y component must be 0. Y is not changing. Every single point along my line is going to have a y component of 2. So the contribution of the direction vector as far as the y component is concerned is nil, it's 0. Okay? My x and my z can actually be whatever I want as long as their ratio is 2. So there's my delta x, there's my delta z, and that's my delta y. Because that's what your direction vector of your line is. It describes a change. You have a point, and now you want to move along your line, so you want to change your point. How are you going to change it? And your direction vector describes your change. I didn't have to make delta x equal to 1. I could have made delta x equal to 2, and then delta z would have been 4. Doesn't really matter what you make it, as long as their ratio is 2, because that slope, that dz by dx equals 2, refers to the ratio between your delta x and your delta y. Question? Yes. Yeah. Absolutely. Yeah. And I think that answers the question. What was the wording? It says to find the parametric equations, plural. Okay, so if we strictly want to answer the question, we'd say x equals 1 plus lambda, y equals 2, and z equals 13 plus 2 lambda. There we go. That would be a strict answering of the question. Yeah. Okay. Of course, I could find the curve of intersection the way we were doing about a week ago, which is how would I do that? I'd plug in my y equals 2 into that. I'd get z equals x squared plus 12. I would parameterize that. I'd say let x equal to t, and then z would equal t squared plus 12. My y would be 2, and that would be my curve of intersection parameterized. That would be my r of t for the actual curve of intersection. And then to find the tangent, I'd work out r dash and go on from there. Okay, so that is how we would have done it a week ago. And of course, it's still perfectly pertinent. But this is basically I don't know, is it a shortcut? It's an alternative way of working out tangent lines to curves of intersection. It does require that one of the surfaces be x equals constant or y equals constant. So this technique is only available to you in that special case. Okay, are you happy? If I gave you one of those now, would you be able to do it? Why not? So several people said no. Why not? Which is the part that's the difficult part? If I gave you 5 minutes to study it and then gave you one, do you think you'd get it? I don't think I heard any no's there. Okay, I'm not going to give you one to do in class now, but if you exercise 84 is assigned to the tutorial this week, and it has something like that. Then there's a couple of homework problems. And moving on to higher order partial derivatives. Okay, so are there any questions about this example before I move on? Yes. I set it to 1. So the question was, how did I get delta x equal to 1? Delta x can be anything. But you need to choose something, and then the delta z follows from that. So I could have made delta x 2, and then that would be 4. I could have made it a half, and then that would be what? 1. Okay, all right. Okay, higher order partial derivatives. Please keep quiet. Please keep quiet. Please keep quiet. Okay, higher order derivatives are when you differentiate and then you differentiate that derivative. And of course you can keep on doing it. So second order derivatives are when you differentiate once and then you differentiate a second time. Third order, of course, would be 3 times, etc. And you can have umpteenth, you can differentiate your function as many times as it will allow. So there's a couple of complications here. Or by complications I mean more complicated than higher order ordinary derivatives. The first one is when you only have one variable, then there's only one possible second derivative because you differentiate with respect to x and then you differentiate with respect to x again. But when you've got 2 variables, you have 4 possible second order partial derivatives. There's the one where you do x and then x again. There's the one where you do y and then y again. There's the one where you do x and then you do y. And then there's the one where you do y and then you do x. So suddenly you have 4 partial derivatives. A nice thing, though, is as long as everything is nice and well behaved, your xy and your yx1 actually end up being the same. So in a sense, you only have 3. But you have 4, really, and 2 of them are generally the same. Okay, and then there's notation that comes along with that. And so here's the second tricky bit, which is that the curly D notation and the subscript notation have a very major difference with one another, and you need to be aware of that. So, higher order partial derivatives. Differentiate with respect to x, then x. The curly D notation looks like that. Okay, that's not too bad. That's what we'd expect, really, because that's how we used to write ordinary derivatives. And here we just have two little x's as subscripts, okay? So far so good. That doesn't look terribly surprising. What about y, then y? Well, doesn't need much imagination to see what's going to happen there. Okay, here comes the big difference. X, then y. That sounds important. Okay, here's the big difference. Okay, that is not me making a mistake. So the F notation, in a sense, is, well, they follow a different logic. The F one, you're basically writing down the letters in the order in which you're doing them. So if you differentiate with respect to X first, and then the second time you differentiate with respect to Y, then you have XY. Okay, X comes first, Y comes second. The curly D notation seems to get that backwards. But the reason why is because it's like this. If you differentiate with respect to X first, then there you go, there's your X derivative. And now you want to differentiate that with respect to Y. If you differentiate with respect to Y first, and then you differentiate with respect to X, it looks like that. And that is why you get the variables in what looks like the wrong order. It's because when you write down your differential operator, that d by dx, that's a differential operator. An operator in mathematics is something that operates on something. It doesn't really have an existence by itself. It exists to act on something. Like the word cos, you'll never see cos by itself. It's always cos theta, or cos t, or cos x. It's cos something. Log, the same. Lim, the same. They're well, maybe limit is slightly different. But those are operators. They operate on things. So d by dx operates on things, and you write it on the left, and the thing it's operating on is on the right. So if we were going to do a third derivative, if we were going to differentiate with respect to, say, w, well, then d by dw would come on the far left. And our letters at the bottom would actually read w, then x, then y. In that order, if we're reading from left to right. Okay, so this is a big difference, and I want you to be aware of it. Okay, but if you can manage to figure out the notation, well, then that's the hardest thing. I want to demonstrate exercise 87. What's the time? Okay, oh, we've got lots of time. Wow, we're getting a lot done today. A. Okay, all right. This is going to be busy. So we have to work out the x derivative and the y derivative first, and then we move on to our second order derivatives. So the x derivative, let's have a look. That's going to be a product rule because we have a product of two functions of x. There's the x squared and there's the e to the xy. Remember that the derivative of e to the xy will be y e to the xy, because the derivative of e to a function is e to that same function times by the derivative of that function. And the derivative of xy is y, as far as x is concerned. What about the y derivative? Well, the y derivative doesn't see that as a product rule, because x squared is not a function of y. It's just some fancy looking constant as far as y is concerned. So we don't need product rule. We're just going to get x cubed e to the xy, because the derivative of e to the xy from y's point of view is x times e to the xy. Everybody happy with that? And then we move on to the second derivative. Oh my goodness, xx. That's So my x derivative has two terms in it, and each of those terms is a product of functions of x. So I'm going to have two product rules. Let me check myself. Yes, I believe that's correct. You could take the e to the xy out as a common factor. In fact, let me do that because it does tidy it up a little bit. Two of the terms are actually the same, so I can add them together. There we go. There's my xx derivative. How about my yy derivative? No product rule going on there. There we go. The yy derivative is quite nice and simple. How about the xy derivative? So the xy derivative is x first, then y. Okay, so in other words, I take my x derivative and I differentiate it with respect to y. Let's have a look. My x derivative has two terms. And as far as y is concerned, only the second one is a product. So let's have a look. What are we going to get? We're going to get 2x squared e to the xy plus, okay, now product rule, x squared plus, and then we bring an x down and it's x cubed y e to the xy. Let me just do that again, make sure I didn't make any mistakes. X derivative, and we want to differentiate with respect to y, so I'm bringing an x down to x squared, and then x squared, and then, yes, I'm confident that that is correct. I could take out the e to the xy as a common factor. Yeah, that wouldn't be too bad. Okay, I'm going to do the yx derivative. So y first, then x. I'm going to take my y derivative and differentiate it with respect to x. Let's have a look. My y derivative with respect to x, it's a product of two functions of x. So product rule, 3x squared e to the xy plus, with respect to x, you bring a y down. Okay. And it in fact is the same. I want to find out, it's named for somebody. Oh bother, I don't have it in my notes here. These two are almost always the same. These are the same as long as they are continuous. Which they usually are. So it really is pretty ordinary for those two things to be equal. And that's actually a theorem that's named for somebody, and I wanted to tell you the name, and I don't have it in my notes. And I don't have it in my head. What I wrote x first, then y. I must admit it does look pretty squiggly, doesn't it? Let me rewrite it slightly more nicely. So let me talk you through what I did there. First of all, I worked out my two first derivatives, my x derivative and my y derivative. And then, slowly and carefully, I worked out my 4 second orders. So one of them, I take my x derivative, which is there, the second line from the top of the screen. I take my x derivative and I differentiate it with respect to x. And that gives me my derivative that has the two little x subscripts. I did it slowly and carefully. It involved product rule, and it's very easy to slip up and to start thinking that y is your variable, not x. So just slowly and carefully. And then similar story for the y derivative. I took my y, my first derivative with respect to y, differentiated it with respect to y again. It was the simplest of all of them. Then these two that are at the bottom, the xy, I took my x derivative and differentiated it with respect to y. And then this one at the bottom here, I took my y derivative and differentiated it with respect to x. Now, I've told you that they're almost always the same. I still would recommend that you do each of them, because if you made some silly mistake in your first derivative, it will become apparent here, because these two bottom ones will end up not being the same. So it's a little bit of a way of checking yourself. So I would recommend that you do work them out independently, but it's quite surprising if they're different. Question towards the back.
The first order.
Hmm?
The first one, the one that you take. When you say x first and y,
Yes.
the first order of x.
Yes. Correct. So you talk about the notation, how the notation works. Yeah. For the F notation, the letter that's written first is the first derivative, the thing that you differentiate with respect to first. And the letter that's written second, the variable that's written second, is the variable that you differentiate with respect to second. So it's in the same order that you read. It's the reading order is the differentiation order. Okay. I've got 3 minutes left according to my notes. Okay. Yeah? The first derivative gives you a slope. Your second derivative gives you, well, your x, so, all right, there's one more thing I wanted to do, but I'm not going to have time if I'm saying this, but I should say this because it's important. So let's think about what these second derivatives tell you. So your x derivative, so say you've got some surface. Your x derivative says, we're going to slice through the surface at constant x, and we're going to look at the slope of the curve of intersection. That's what your x derivative is. It's the slope of that curve. So your x derivative is the concavity of that curve. Your y derivative says, okay, we've got the surface, we're going to slice through at constant y and look at the curve, and my y derivative is the slope of that curve. Okay? And my y derivative will be my concavity. But it's frequently the case, of course, that your first derivatives, and it is in this example, that your x and y derivatives are both functions of x and y. Okay, because we're still dealing with a surface that has changing x and changing y. And when I say we slice through at constant y, it could be any constant y. Okay, all right, but still, your x derivative and your y derivative are not too problematically interpreted as concavities.